Hello friends and welcome to the third lecture in module 3, that is application of critical flow. The learning objectives are that we will be applying the specific energy and critical depth concepts for flow measurement. We'll also understand what are the effects of raising the channel floor or constricting the channel width on flow conditions, and using the combination of both these we'll try to understand the concept of choking of flow. So we discussed in the previous class that the attainment of critical flow condition is important because there we get a unique depth discharge relationship and which can help in measuring flow. So based on that principle, many flow measurement devices have been developed, or so-called hydraulic structures, which are applicable in field. Now in such device, how the principle works that the critical depth is created either by constructing a low hump in the channel bottom, that is usually called a weir, or by contracting the cross section such as critical flow flume or venturi flume. So many, if you see along the highways, there are culverts and flumes which are developed in canals also. They are used to measure flow in canals, and as well the culverts will help us gauge the water which is coming as runoff from the nearby agriculture fields. So these are the two main flow measurement strategies been adopted, which are based on the concept of critical flow. So we'll go with the first one, that channel with a hump. So again, in this we'll discuss two cases, one for the subcritical flow which is entering the channel, and one is supercritical flow. So in subcritical flow we can see that this is the sketch where a hump is provided in the channel. So that hump is having a height delta z. So at there are two sections, section 1 and 2. So we'll be measuring depth at both the sections, and then we'll be applying specific energy concept. So we are considering a horizontal frictionless and rectangular channel of width b and carrying discharge q, having an upstream depth of y1. So the specific energy at section 1, that is E1 is equal to y1 plus v square by 2g, and at section 2, so this is the specific energy remains constant, so this hump will be subtracted. So E2 is E1 minus delta z, so that is the height of the hump. So there can be three cases where we will deliberate this discussion. So in the first case, your height of the hump is less than delta zm, that is the maximum height that can be permissible. So let us understand with the help of specific energy diagram. So initially, if your water surface is at point P, so when you go on increasing the height of the hump delta z, that it tends to zm, delta zm, there will be reduction in the specific energy E2. So E2 will go on reducing. So in this case, your point on the specific energy will shift from point P to point R. So that means your specific energy E is decreased by an amount of delta Z. So the depth y2 over section 2 of the hump, that is the specific energy at that point, is given by E2 is y2 plus v square by 2g, and that is y2 plus q square upon 2g b square y square. So this generally gives us a picture that as your delta z will increase, your y2 will decrease. So you can see that the y2 initially was at this point, now it is reduced to this. So the y2 will go on decrease, but your y1 will remain unchanged. Okay, so let us go to the another case where your delta z is equal to zm. Now in this case we can observe that your point, from it was transiting from P to R, now it will further transit and it will eventually meet the critical point when your delta z is equal to zm. So at that particular instant it will meet the critical point. So critical depth is established at section 2. So your y2 will become yc and e2 will become ec. Okay, so at this point, your delta Zm, that is the maximum height of the hump, which is possible without changing the upstream flow depth. So with the help of these information, your E1 minus delta Z, that is equal to E2, that is equal to EC, because critical flow is there, that is YC plus Q square upon 2GB square YC square. So that is the condition available. Now, so what we observe, that your depth at section 2 becomes critical depth, and delta Z becomes delta ZM, that is the maximum height of the hump, and Y1 is unchanged. Now coming to the third case, this is more interesting in compared to other two cases. So what happens here? So let us consider here your delta Z is greater than delta ZM. So if your delta Z is greater than delta ZM, that means it will encapture this territory of the specific energy curve, and it has to, the point has to fall somewhere here or here. But as we have seen earlier also, that any specific energy less than the critical specific energy, the flow is not possible for the given conditions. So that thing again happens here, that the flow is not possible for any height delta Z greater than delta Zm. Now in order for the flow to happen, your specific energy E1 would change to E1 dash, and the increase in specific energy means your depth of flow would increase, and that means from point P it has increased to point P dash. So your depth has again increased to Y1 dash. So in order to entertain flow in such condition, the upstream flow conditions would change, while at downstream you will still have your critical flow conditions. So the new specific energy at section 1, that is given by E1 dash, that is equal to Y1 dash plus Q square upon 2GB B square, this will be B square Y1 dash square. So in this case, your E1 dash is greater than E1 and Y1 dash is greater than Y1. So this E1 dash is just enough to pass the discharge over the hump where the critical flow conditions happen. So again at E2, that section 2, you have critical flow condition. So E2 is equal to EC, that is equal to YC plus Q square upon 2G B square YC square, that is E1 dash minus delta Z. So what we see in the third case, that when your delta Z is greater than delta Zm, at section 2 you have critical depth, but at section 1 your depth changes or rather increases to Y1 dash. So let us summarize all these three cases. So in case 1, you can see that at section 1 the depth remains unchanged. This is the height of the hump delta Z, and your Y2 here is greater than YC. Now second case, when delta Z is equal to Zm, your Y2 becomes, so you're gradually increasing the height of the hump. So Y2 is YC, so your critical flow happens over the hump, and Y1 is still unchanged. But at section 3, in the case 3, when your delta Z is greater than delta Zm, the flow does not happen in the given conditions, and a change in the conditions are warranted, and that is why your upstream depth increases to Y1 dash, while your downstream remains the critical depth only. So this is what can be summarized for the subcritical flow, and a graph here shows the same variation. So these are two curves, one related to the sub depth y1 and another related to depth y2. So what happens to depth y1? That in first case it is unchanged. Again at second case is this point. So this line represents the second case. So again it is unchanged. In third case is it undergoes an increase. Now in case of depth y2, at first case it will decrease and it will reach yc. In second case it is constant at yc, and third case again it is constant at yc. So this is a very important diagram summarizing all the three cases. So let us compute what is the minimum height of hump that is required for critical flow to happen at section 2. So again our assumptions carry on, that it is a smooth, frictionless and streamlined hump placed in a rectangular channel, and it is carrying a subcritical flow. So with the help of that relationship, you get that E1, that is equal to E2 plus delta Z. So that relationship we have. So now delta Zm, that will give you the minimum, the height of the hump that would cause critical flow at section 2 without changing the upstream specific energy. So this is the minimum height which is required to generate the critical flow. So our equation 7, by modifying the conditions that delta Z is equal to delta Zm, and E2 is equal to EC, that is a critical flow, that is equal to 3 by 2 YC. So your E1 is equal to EC plus delta Zm. So this is the modified form of equation 7. Now making delta Zm as subject, it is E1 minus 3 by 2 YC, that is Y1 plus V1 square by 2G minus 3 by 2, and YC is nothing but Q square by G raised to 1 by 3. Now this Q is equal to again V1 into Y1. So again modifying this equation, that will be 3 by 2 V1 square Y1 square upon G the whole raised to 1 by 3. So let us divide equation 9 by Y1. So after dividing by Y1, we get delta Zm by Y1 is equal to 1 plus V1 square by 2G Y1 minus 3 by 2 Y1 into V1 square Y1 square upon G raised to 1 by 3. So if you closely look, this equation comes to the form where V upon under root Gy can be written as Froude number, that is upstream Froude number F1, and the equation gains the form that delta Z m by y1, that is equal to 1 plus f1 square by 2 minus 3 by 2 f1 raised to 2 by 3. So if you want to find out what is the height of the hump, so with the help of the Froude number itself and the upstream depth, these two parameters will help you find what is the minimum height of the hump that is required. Now proceeding our discussion to supercritical flow. Now, in case of supercritical flow, the discussion remains same, only the signs will change, because initially, so if let us say a depth y1 was increasing in supercritical flow, it will decrease in, sorry, depth y1 was increasing in subcritical flow, it will decrease in supercritical flow, and same for depth y2. So that changes happen. So let us understand what happens in case of a supercritical flow. So in case of supercritical flow, your flow initially is at point P double dash. So there will be rise in your supercritical depth from P double dash to R double dash. Okay, so specific energy E2 is E1 minus delta Z. Now since the flow is supercritical, there will be a drop in the specific energy would cause the rise in the water surface. So let us see further. So you can see that any drop in the specific energy, that would lead to the rise in the water surface. So again, three cases are possible in this. So the first case, this is your supercritical flow. So that is why the depth is less, and this is the hump. So your depth y2 is less than the critical depth. So y2 would increase as your delta z increase, y1 remains unchanged. At case 2, where delta z is equal to delta zm, your y2 becomes critical, and your delta z, that is equal to the delta zm, that is the maximum height of the hump which can be provided without changing the upstream conditions. Again your y1 remains unchanged. Now in the third case, what happens that when your delta z is greater than delta zm, your y2 is equal to yc, and y1 would decrease to y1 double dash. So there is a reduction in the upstream flow depth. Now this specifically needed because your specific energy is increased, and it would be required to negotiate the hump. So in this case, so I have already sketched the how that transition will happen from supercritical to subcritical. So a hydraulic jump will take place essentially. Okay, so whatever I've sketched is the tentative location of hydraulic jump. It may vary depending upon the actual discharge and other conditions. So since the hydraulic jump comes into picture, this case cannot be analyzed only with the help of your energy equation, and you may require even the specific force concept to analyze this particular case because of the hydraulic jump. So similar to the subcritical case, you have again the variation of depth. So as you can see, y2 will initially increase, then it will become constant, and to a point that is equal to yc, and depth y1 is constant initially, but when your delta z is greater than zm, it will drop. So that is what is happening for the subcritical flow. Now, what application we perceive from this? So there is a flow measuring device which is called a broad crested weir. So what happens essentially that you raise the height of the floor, that is greater than equal to delta z, and it has sufficient length over it so that the critical flow and parallel flow can occur, and this conditions would help us gauge the flow over the broad crested weir. So the broad crested weir, so this is the schematic of a broad crested weir. So you can see this width is sufficient. So in broad crested weir there is some change in the nomenclature. This is termed as the width, and whatever is transverse to the flow, that is termed as the length. So your parallel flow should occur at along this width, and the critical flow where it is critical flow criteria is met, at that point your critical depth will be there, and you will also measure the depth upstream, that is h. Okay, that is above the floor of the weir, so that is h. So h is equal to yc plus vc square by 2g, that is equal to 3 by 2 yc, and using this you finally get a equation small q, that is equal to 1.705 h raised to 3 by 2. So that means your discharge per unit weight is a function of your head upstream. So in case of a broad crested weir, you just measure this head h upstream of the weir, and you can simply calculate what is the discharge passing over the weir. So total discharge is small q into L, where L is the length of weir in the transverse direction. So in fields, we can see the application of broad crested weir for flow measurement. Next part comes to the transition with a change in width, that is constricting the flow width. So in this case, again, we have the subcritical and supercritical flow discussions. So our assumption is we have a horizontal frictionless rectangular channel of width B1. So the upstream width is B1, and it is carrying a discharge Q at depth Y1. So as you go to downstream, a smooth transition is provided and the width is reduced to B2. So that is in plan, and in section also you can see the same thing. So what water level changes happen? So in the upstream section, using the width B1, you get the specific energy E1 is equal to Y1 plus Q square upon 2G B1 square Y1 square. And in the downstream section, E2 is equal to Y2 plus Q square 2G B2 square Y2 square. So these are the specific energy at section 1 and 2. Now we can substitute this, that small q 1, that is equal to q upon b1, and small q2, that is q upon b2. So since b2 is less than b1, so q2 will be greater than q1. So the downstream width is smaller, so discharge per unit width will be naturally larger. Now let us understand the specific energy diagram, what changes happen. So at section 2, your E2 is equal to E1 and Q is equal to Q2. So at so the point P would move vertically downward on the curve to a point R on the curve Q2, that will reach the depth Y2. So it will reach a depth Y2. Now in subcritical flow, your Y2 is less than Y1. So if you go on reducing the width B2, your again discharge will increase that much, because this is inversely related to your width. So the more you reduce the width, this discharge would increase, and consequently this Y2 will decrease. So it will go on decreasing. So you can see these are the curves for small q. So as the small q would increase, it will go on falling on this particular curve, and that would result in decrease of the y2 depth. So the limit of the contracted width, so in case of hump also we had a limit that you can increase the height to this particular level. So limit of the contracted width here So that is B2 is equal to Bm is reached when Q2 is equal to Qm for a given specific energy E1. Now at this juncture your minimum width is achieved, that because you cannot constrict less than B2m, so your Y2 will be equal to YCm. So section 2 will develop critical flow condition, and your specific energy E1, that is equal to ECm, that is for the critical flow, that is YC plus Q square upon 2G B2m, because at section 2 you have critical flow condition into YCm square. Now for a rectangular channel, you know YC is equal to 3 by 2 EC. So Y2 will be YCm, that is 2 by 3 ECm, and that is equal to 2 by 3 of E1. So simplifying this, you get YCm, that is equal to Q square upon G B2m square, and your B2m can be obtained as under root Q square upon G YCm cube, or 27 Q square upon 8G E1 cube. So either you have the specific energy or you have the critical depth. Based on that, you can find what is the minimum width constriction that is possible while maintaining the critical flow at section 2 and without changing the upstream flow conditions. Okay, so that's simple. So let us understand the case, that is, so here in the first case your B2 is greater than B2m. So this is greater than B2m, that is the minimum width required. So for subcritical flow the Y2 depth will be less than the Y1, so and it is again less than your and greater than your YC. However, Y1 remains unchanged. In second case, when B2 is equal to B2m, so at that point the critical flow conditions developed at the section 2 and your Y1 is still unchanged. But in the third case, where your B2 is less than B2m, that is you go for very high constriction, that is in that case, although the critical depth is maintained in section 2, but in order to pass that flow there has to be change in the specific energy of the upstream section, and thus increase in the depth Y1 to Y1 dash is observed at the upstream section. So this is what happens in the third case, because otherwise the flow will not be possible. So to make the flow possible, the upstream depth has to change, and that is what is happening in this case. So looking at the equation, new specific energy would be E1 dash, that is Y1 dash plus Q square upon 2G B1 square into Y1 dash square, and the critical depth at section 2 YC2, that is equal to small q square Q2 square upon G raised to 1 by 3, and the specific energy is 1.5 times YC2. Okay, so graphically let us look what changes we can visualize. So on the x-axis it is a ratio of B2 by B1, and this is the width constriction limit, and here you have Y1 Y2 and the specific energy. So you can see this curve is for depth Y1. So depth Y1 is initially going on decreasing, and then it will become constant. So I mean we have to look at the reverse case, sorry. So we look from the right hand side. So depth Y1 is initially constant till this point where you are, because we are decreasing, so we are moving on the lower side. So this curve has to be interpreted from right to left. So depth Y1 is constant till the critical point is achieved at case 2, and in case 3 this will go on increasing. Similarly, depth Y2 in the case 1 it is going on decreasing till it reaches the critical depth at section 2, and again it will go on increasing the depth Y2. So that is what happens in this particular case. So we can see that the depth Y2 increases post reaching the minimum constriction point. However, still it is critical flow conditions. Okay, so now let us move to the discussion on supercritical flow. So in supercritical flow, when the approaching flow is in supercritical, your depth y1 will be less and depth y2 will be more than that. So the reduction in width would cause increase in Q2, and thus there will be rise in Y2. However, Y1 would remain unchanged. As you further go on decreasing the width, your Y2 that will reach a critical point at specific condition when your B2 is equal to B2M. So in that case, where you have reached the minimum constriction point, your y1 again remains unchanged. But when you further try to constrict the flow beyond B2M, so that won't happen under normal flow condition, and that is why the upstream specific energy would change, while at section 2 you will have still critical flow conditions, and a hydraulic jump formation would essentially be observed to overcome this scenario. So let us look at the graph. So here we can see that the specific energy curve variation is also given, that is for E1 dash, and the depth variation. So depth y1 till the constriction point it is constant, and then it will go on reducing. Now the depth y2, it is increasing till that point. It reaches this point yc, that is case 2. This is your case 2, and apart from case 2, it will further go on increasing gradually, but still it will be critical flow at all these times. So this is the variation of depth y1 and y2 when we resort to flow constriction in case of a supercritical flow. Now there comes a special case where, let us say, if you simultaneously raise the hump and simultaneously reduce the width, so you are reaching that particular point where both the effects are happening parallel. So in that case, uh, we observe that the upstream water level is not affected until the critical stage is reached. So that means the critical stage is very important in this case. So let us recall how these two effects can be merged and visualized. So in case of hump, we have observed that when delta z is less than delta zm, the upstream depth is not altered. Okay, so in case of wedge constriction, for all cases where B2 greater than equal to B2M, your upstream depth again is constant. Now, as soon as your B2 becomes less than B2M, the upstream depth undergoes a change. Now, the onset of critical condition is a prerequisite to choking. So that means your flow should have reached case 2 in either case, where you go by delta Zm or B2M. Case 2 should be reached so that you have critical flow, and then only choking can occur. So any flow condition where your delta Z is greater than delta Zm and B2 is less than B2M, these are known as choke condition, and that means your flow will not be able to pass through the either culvert or the canal, and that condition is undesirable, and we need to specifically monitor that when we are designing the culverts. So when you, because what happens that the natural river way you constrict in order for your water to pass through that culvert due to economy reason, so we just constrict the width. And if there is a raising of floor because the river bed is uneven, so in order to make that culvert section prismatic, you construct it such a way that you raise the floor also. So that particular case, here the application of choking condition is very essential. And coming to the last part, that application of this width constriction in flow measurement. So as we discussed that the Venturi flume, so there are it is a case in a critical depth flume. So the in critical depth flume, control section is achieved, that is specific depth discharge relationship by width constriction. So the constricted portion, this particular portion is called throat, and there is a diverging section also. So the hydraulic jump is formed in the downstream part. So here you can see that this is the constricted section, and sometimes the hump is also provided in order to form the hydraulic jump in the downstream. So this constriction flume, if the flow conditions are subcritical, then it is called Venturi flume. And how do we measure discharge in case of a Venturi flume? So again the formula is same of the broad crested weir, that is Q is equal to 1.705 H1 raised to 3 by 2, and by measuring the upstream water depth we can find out what is the discharge passing through that culvert or any other structure by means of a Venturi flume. So your H1, again it is a difference in water surface elevation upstream of the inlet, which is measured from the top or the crest of the throat. So if the hump is provided here, so from its top it is measured. So in practice, these flumes are widely used in water treatment plants and in irrigation fields. So with that, we complete the critical flow part. So we discuss its concept, specific energy. Then we discuss the computation of critical depth, section factor, hydraulic exponent, and now today the application of critical flow. So in the next lecture, we'll be starting with the non-uniform flow, that is the gradually varied flow. Thank you everyone and have a nice day.